Hello and welcome to this revision session where we're going to look at the topic of waves in AQA A-level physics. So in today's revision session, our learning objective is to answer examination questions on the waves topic of A-level physics. So if we've been successful and we've learned in this lesson, we should be able to answer A-level physics examination style questions, you should be able to assess your understanding on A-level physics, and finally understand what topics we need to improve upon for A-level physics. So how do you prepare for this revision session? So when completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and then on the left hand side write down your working out and answers to the questions in the revision session. Now when you're doing this, make sure you're writing full sentences and show your full working out, whilst in the right hand side write down any pieces of information which you find useful or any hints and tips on answering questions from this revision session. At the end of the revision session, I would advise that you write up these notes into a revision sheet for you to revise independently. So what tips do you have for revision? So how can you be independently revising your A-level physics? So the first step is always to use your revision guides, use the class workbooks, your prep notes, your textbook to learn the key ideas of the course, learn the key facts. Now you might want to do this by making mind maps or writing notes out yourself. The second step will be to test yourself. So use things like Caboodle, Seneca, knowledge checkers to quickly test your own knowledge, and you might want to do this by making your own cue cards. And then finally, practice examination style questions by using examination prep books, homework books, supervised study books, additional workbooks to help you answer examination questions and then mark your own work. And to do this, you might want to download your own examination papers to do this. So the three steps of learn the key facts, testing yourself, and then practicing examination questions are how you should be revising physics independently. So let's have a look at some multiple choice questions on waves. So let's look at the following question. In the derivation of the diffraction gradient equation n lambda equals d sine theta, a diagram similar to one below can be used. Which of the labelled angles alpha, beta or gamma is equivalent to the angle theta in the equation? So pause the video now. Then unpause the video when you want to go through your answer. Right, so what you've got to understand is that when you're looking at the equation n lambda equals d sine theta, okay, that the angle alpha is the angle given the equation, because this angle of theta is the angle measured from the normal of the slit. But beta is also a possible answer, because if you consider similar triangles, you notice that alpha and beta are actually going to give you the same value. So the answer there was B. Next question. A pulse of white light passing along the axis of a straight optical fibre. The pulse is broadened when it leaves the optical fibre. So what causes this particular effect? So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to understand what absorption, attenuation, material dispersion and modal dispersion are. Now straight away, absorption and attenuation won't be the correct answer because we're considering the idea of the pulse actually broadening, which means that the wave is spreading out, the signal is spreading out. Now the answer is C, because material dispersion causes the signal to spread out as it travels through a material, which then leads to the concept of pulse broadening. Our next question is that light crosses the boundary from air into a substance that has a refractive index of 2. Now what happens to the speed, the frequency and the wavelength of the light as it crosses the boundary? So pause the video now, then unpause the video when you want to go through your answer. Right, now the first thing you've got to remember is that in refraction, the frequency remains constant. So the answer is either going to be A or B. Now your answer in this instance is A, because if an object is going to a higher refractive index, then it must be slowing down, because it's going into a more optically dense material. Now we know that the actual denseness optically of the material has doubled because air has a refractive index of 1 and this substance has a refractive index of 2. So if the density optically of the material has doubled, then the wave is going to slow down and therefore its speed will halve. Now the wavelength will also halve due to the wave speed equation, because we know wave speed is equal to frequency times by wavelength. So if the frequency remains constant and the speed halves, it means the wavelength must halve as well. Let's now have a look at our next question. A stationary wave forms on a string when progressive waves are reflected at fixed ends. For a real string, energy is transferred from the progressive waves when they are reflected at the fixed ends. The effect of this energy transfer on the stationary wave is that. So pause the video now, then unpause the video when you want to go through your answers. Now, the important thing you've got to note is that when they're reflected in the real world, you won't get this exact interference pattern where you'll get complete nodes and you get complete antinodes. So it's not that the nodes and antinodes no longer form, but rather the answer would be B, that the nodes would not be positions of zero amplitude, because you won't actually get the two waves completely cancelling out, so they wouldn't go to exactly zero. So our answer in that instance was B. Let's have a look at our next question. Ray X is instant on one slit and ray Y is instant on another slit of a double slit arrangement as shown below. A fringe pattern is not observed on the screen. What is the possible explanation for this? So pause the video now, then unpause the video when you want to go through your answer. Right, now it's important again to note that to get a fringe pattern on a screen, that the waves must be interfering with each other to cause this fringe pattern. Now, to get waves to interfere, you need to have the rays be coherent with each other. Now, the definition of coherent is that the waves have a constant phase difference and they have the same wavelength / frequency. So the answer here is X and Y do not have the same wavelength, so you can't have coherency, so you don't get an interference pattern forming. So our answer here is B. Next question. Light of wavelength 500 nanometers is instant on a double slit and the resultant fringe pattern is shown below. V is the central bright fringe and the dark fringes are shown shaded. What is the path differences that results in fringe W? So pause your video now, then unpause the video when you want to go through your answer. Right, so it's important to note that W is a second order dark fringe. So this means that the two waves must be out of phase with each other and so must have a path difference of an odd number of half wavelengths. Now, because this is a second order fringe, as we'll notice because it's not one of the central ones but it's a second order one, the path difference is therefore going to be 2.5 wavelengths, because our equation to work out the path difference of which causes destructive interference is going to be 2n plus 1 over 2 wavelengths. So therefore that tells us that we're going to have 2.5 wavelengths, which gives us 1250 nanometers, resulting in our answer of A. Let's now have a look at a few longer style questions to do with waves. So the first question is, laser light is instant normally on a diffraction grating. The diffraction grating has 250 slits per millimeter. A third order maximum is observed at an angle of 29 degrees to the central maximum. Calculate the frequency of the laser light. So pause the video now, then unpause the video when you want to go through your answer. Right, so first thing you've got to note is that in the equation you want to be using n lambda equals d sine theta, but d needs to actually be calculated very carefully because it's not 250. The first thing you would need to do is you need to work out what the actual distances between the two slits are. So if there's 250 slits per millimeter, the distance in meters between two slits is 1 over 250 times 10 to the 3, because you've got to work out how many slits are actually in 1 meter. So it's 250 times 10 to the 3. So therefore you get your answer, you get your value for d, you then plug this into the equation n lambda equals d sine theta, and you make lambda the subject. You say lambda equals d sine theta over n. We know what theta is. It's 29 degrees from the information given in the question. We know what n is because it's a third order one, so we get our value to be 6.5 times 10 to the minus 7 meters. We then use speed equals frequency times by wavelength to then work out frequency, because we can say frequency is equal to 3 times 10 to the 8, we know that because it's laser light, so it's a light wave, divided by our value we've just worked out for lambda to get our answer to be 4.6 times 10 to the 14 hertz. Let's have a look at our next question. A student is provided with the following apparatus: a lamp, a polarizing filter, and a light meter that measures the intensity of incident light. Describe how the student could use this apparatus to determine whether the light coming from the lamp is polarized. So pause the video now, then unpause the video when you want to go through your answer. Right, now the first thing to note very importantly is that to observe if polarization takes place, you've got to be rotating your filter. So what you would need to have is you need to have a lamp on one side, a filter in the middle, and then the light meter on the other side of the filter. So that's our setup, which we can observe and monitor intensity during rotation. So as we rotate our filter around, if polarization is present, the intensity will vary, but it would not vary if it was not polarized. Now it's important to know that as it's rotated, you should see a maximum and minimum occur if you've got a polarized bit of light, because if the polarized light is in alignment with the filter, all of it should go through. But if it's 90 degrees out of alignment, you should get nothing going through. So you see your maximum and your minimum. Right, let's have a look at another question. So a progressive wave transfers energy along the wave, but stationary waves do not. So describe two other differences between stationary waves and progressive waves. So pause the video now, then unpause the video when you want to go through your answer. Right, so how can you answer this question? Now you've got to think of what the actual characteristics of stationary waves and progressive waves are. So you could say that stationary waves have nodes and antinodes while progressive waves don't. You could think that in a progressive wave the phase will vary continuously across all the points, but in a stationary wave all the points between the nodes which are next to each other are all in phase. Also, in a stationary wave, different points in your stationary wave have different amplitudes, but the point of a progressive wave is that all the points have the same amplitude because it's progressing through the substance. Let's have a look at our next question. A string of mass 0.98 grams vibrates between two fixed ends, x and y. The distance between x and y is 0.612 meters. The tension in the string is 69 newtons. Figure 1 here shows one position of the string when vibrating at the third harmonic. So use this to determine the frequency of the third harmonic. So pause the video now, then unpause the video when you want to go through your answer. Right, so with this equation we're going to be using the equation for a vibrating string, which is F is equal to 1 over 2L times by the square root of the tension over the mass per unit length. So you've got to now firstly work out what the mass per unit length is by doing the mass in kilograms divided by the length of the string in meters, which we are given both values, although we're given the value of mass in grams, but we can work it out in kilograms in the actual question. Now as well, it's important to note that because it's the third harmonic, okay, that when you've worked out your value for frequency in that equation, you've worked out the fundamental frequency. So to work out the frequency of the third harmonic, you've then got to multiply the frequency by 3, because the value you get in the equation F equals 1 over 2L times by the square root of T over mu, when mu is mass over length, that is going to be the frequency of the fundamental frequency, which is the base value there. So to work out your then harmonic, you then multiply by the harmonic number. So because it's the third harmonic, therefore it's going to be tripled. So the answer is going to be 509 or 510 hertz. Let's have a look at the next question. So figure 8 shows the apparatus a student uses to investigate stationary waves in a stretched spring. Two small pieces of adhesive tape are fixed to the string as markers P and Q. Markers P and Q are 0.55 meters apart and an equal distance from the ends of the string. A graph paper grid is placed behind the string between P and Q, and you'll notice that they're, like I said in this picture, they're 0.55 meters apart. So the string is made to vibrate at the second harmonic. So how would the motion of P compare with that of Q? So pause the video now, then unpause the video when you want to go through your answer. Right, so how can we consider this particular idea? You'll notice that P and Q are going to be in antiphase or completely out of phase. So our phase difference is therefore going to be pi radians. Now they will have similar amplitudes of vibration because they're in the same wave, okay, but so there'll be a similar displacement, okay, and they should have the same frequency and the same period, and they should again move with the same speed. Now it's important to know that if you're asked to describe about motion, you're asked to describe about wave properties at particular points, talk about the phase difference between the 2 points, but also compare your amplitudes, compare your frequencies, and compare your speeds. Let's have a look at the next question. The frequency of this vibration generator is then increased, and a higher harmonic of the stationary wave is formed. Figure 9 shows the string between P and Q at an instant in time. The dashed horizontal line indicates the position of the string at rest when the vibration generator is switched off. Now the frequency of the vibration generator is 250 Hz. Calculate the wave speed. So pause the video now, then unpause the video when you want to go through your answer. Right, so what we've got to consider is as follows, that we want to use the equation V equals F lambda to work out what our value of V is. Now you can use this to determine what the wavelength is. Now you'll notice that between P and Q that this isn't actually one wavelength, it's actually two wavelengths between the two of them. Now you'll notice that because it's gone from a P to a peak and then from another peak to Q, which is the next peak along. So the distance between one wavelength is from peak to peak, or similar point to similar point on the next wave. So therefore it's going to be half of 0.55 meters, which is 0.275 meters. We know what our frequency is, it was given in the question. We multiply the two values and we get 69 meters per second. Again, that's an appropriate estimation, you would think, for the speed of a standing wave on a string. Let's have a look at our next question. The instantaneous position of the string in figure 9 can be explained by the superposition of two waves. The instantaneous position of these waves between P and Q is shown in figure 10. Describe the properties that the wave must have to form the shape shown in figure 9. So pause the video now, then unpause the video when you want to go through your answer. Right, so what's important to note here is that if you look at these two pictures, you'll notice that they have the same speed, however they're now moved in opposite directions, but they have the same wavelength or the same frequency, so you'd say they have the same amplitude. You know this because you can see that in the figure 10, that as a result here, they've got the same height, so therefore they must have the same amplitude, so we've got the same position as of our wavelengths, so we've got, as I said before, same wavelength, same frequency, similar amplitudes. Okay, they are got the same speed, but they are moving in opposite directions. Let's have a look at our next question. The frequency of the vibration generator is reduced until the first harmonic is observed in the string, as shown in figure 13. The string in figure 13 is replaced with one that has 9 times the mass per unit length of the original string. All other conditions are kept constant, including the frequency of the vibration generator and the tension in the string. Deduce the harmonic observed. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you tackle this particular question? Well, once again, you'll use the equation F is equal to 1 over 2L times by the square root of T over mu, where mu is the mass per unit length. So what you'll say is, if you have a look at this particular image, you know that mu has increased by 9. So therefore, when you work out your frequency, it's reduced to actually a third of the previous value, because what you've put in is you've put in mu to be 9 times as big, but it's square rooted, so 9 square rooted becomes 3, and because it's T over mu, therefore it's going to be 1 over 3. So therefore we can say that the frequency has reduced to a third of its previous value. So therefore the speed has reduced to a third of its previous value. So therefore the string must be being driven at 3 times this particular frequency to get this out. So therefore the harmonic which we're observing is going to be the third harmonic. Right, next question. In 1870, John Tyndall sent a beam of light along a stream of water. Figure 4 shows the modern version of Tyndall's experiment using a laser beam. Water has a refractive index of 1.33. Explain why the laser beam stays inside the stream of water. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've been given the refractive index and you've got to understand why it stays inside the stream of water. Now it's going to stay inside the stream of water because it must be carrying out total internal reflection, which is what you'll get 1 of your marks for. Now the second thing you've got to talk about is why it carries out total internal reflection. Now the important thing to note is the refractive index of water is 1.33. We know the refractive index of air, which is what's surrounding water, is 1. So you could say that the refractive index of water is greater than air, because that's actually a condition of total internal reflection, that to get that occurring, the refractive index of the material which carries out total internal reflection must be greater than that of the refractive index around it. Or you could say that the angle of incidence is greater than the critical angle, because that's the other condition which would allow for total internal reflection. Let's have a look at the next question. From the information given, calculate the speed of laser light in the water and calculate the critical angle for the water to air boundary. So pause the video now, then unpause the video when you want to go through your answers. Right, for this first one, what we've got to do is we've got to use the equation refractive index is equal to the speed of light over the speed in that particular material. Now what we know is we know that for water the refractive index is 1.33. We know that the speed of light in a vacuum is 3 times 10 to the 8, and so therefore we can work out the speed in the water by doing 3 times 10 to the 8 over 1.33. So we're now going to work out our value, which is 2.26 times 10 to the 8, and we give it to 3 significant figures. Why 3 significant figures? Because the information we've given in the question, the refractive index, was also given to 3 significant figures. Let's have a look at the next question. How do you calculate the critical angle for the water to air boundary? So you would work out your critical angle with your equation of sine critical angle is equal to 1 over n. So you can work it through like that. You've been given n, you work it through to get 49 degrees. Let's have a look at our next question. Tyndall's experiment led to the development of optical fibres, and figure 5 here shows a step index optical fibre. A step index indicating that there's multiple layers in your optical fibre. Discuss the properties of the step index optical fibre. So your answer should include the names of part x and y, a description of functions of x and y, and a discussion of the problems caused by material dispersion and modal dispersion and how these problems should be overcome. So pause this video now, then unpause the video when you want to go through your answer. Right, so for this one you've got to hit each bullet point individually to make sure you get your full 6 marks. So for the first bullet point, the name of X is the core and Y is the claddon. Now the function of the core is to propagate or guide the light, the wave, through the actual optical fibre by total internal reflection. Now what the properties you would need to know about for the core is it carries a low attenuation and low absorption, because I don't want it to take in any of the information from the light wave, and we need the refractive index of the core to be greater than the claddon, because for total internal reflection to occur, which is how the light will travel through the core, the actual core needs to have a refractive index greater than that of the material that surrounds it. Now Y, the claddon, prevents the core from damage. It prevents crosstalk between touch-in fibres, i.e. it stops the light waves going into different optical fibres and crossing over the information, and it also provides a clean, nice boundary for total internal reflection. Now the problems with modal and material dispersion are as follows. Both of them will cause pulse broadening, and both of them will cause a limited bandwidth. Now material dispersion is caused because different wavelengths of the light will have different speeds, because they'll have different refractive indexes within the core. So that can only be overcome if you use a light of one wavelength. So you've got to send down a monochromatic, because the colour is the wavelength, beam for your information. Whilst modal dispersion takes place because if you've got a low critical angle which will carry out total internal reflection, that gives you multiple paths or modes for your light to totally internally reflect through the actual material. So therefore, that gives you different lengths, therefore different times, that the actual waves are in the core, which can lead to the pulse broadening. So the idea is to do this, you've only got to allow a single mode fibre, only allow one possible pathway for the wave to totally internally reflect through. So that can be done by either having a narrow core, having a small refractive index between the core and the claddon, which would lead to a high critical angle, which would mean that there's fewer paths that the light could possibly take. Let's have a look at the next question. Scientists use optical fibres to monitor earthquakes. The light travelling through an optical fibre can be reflected by impurities in the fibre, as shown in the image. Earthquakes bend optical fibres slightly, and this changes the amount of reflected light. So suggest from the information why the amount of reflected light changes as the fibre bends. So pause the video now, then unpause the video when you want to go through your answer. Right, now there's a couple of different things you can talk about here. The first thing is that if it's now bent, the light can encounter impurities at different positions or angles, which will mean that it won't get through as much, or might get through more. The light can encounter a different number of impurities. It will encounter a different size of impurities because it's now taken a different pathway through the optical fibre. Again, interestingly, we said before that for total internal reflection to take place, your angle of incidence needs to become greater than than your critical angle. Now the critical angle itself can't change because that's a property of the material, but the angle of incidence which the light will go through the core could change because of the earthquake, and if it's less than the critical angle you won't get total internal reflection. Bending might cause the cladding to crack, which would mean that you won't get all the total internal reflection because some light would seep out of the core because of this, and then you might say that the light actually may be refracted more, okay, than it was before because you need it for total internal reflection to actually go through your fibre optic cable. Now, the next question here shows apparatus used to investigate the stationary waves on a string. Now, the frequency of the vibration generator is adjusted until the first harmonic stationary wave is observed on the string, and you then repeat it for different loads. So, show how the frequency of F of the first harmonic is related to the tension in the string by the following equation. F squared is equal to 1 over 4Lm times by T. So, pause the video now, then unpause the video when you want to go through your answer. Right, so how would you do this one? So what you've got to understand is that, like we said before, F is equal to 1 over 2L times by the square root of T over mu, where mu is mass over length. But it's important to note that here we're being given mass and length in the equation. So they want you to change mu in that equation to mass over length. So what you would do is you would square all the terms to get F squared, and therefore you pop in m over L for mu and rearrange it and get the equation which is written down there. The next question is, to measure the length of 2.600 meters, a meter ruler or a 5 meter measuring tape may be used. Both a meter ruler and a tape measure have a 1 millimeter resolution. Explain the advantage of using a 5 meter tape. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to think about what's going on here. Now, you would think about that for the tape measure, there's actually going to be a smaller uncertainty for the tape measure because you're only having to use it once. Now, for a meter ruler, it's going to have a higher uncertainty because you're going to have to move your meter ruler multiple times to measure 2.600 meters, because your meter ruler, as you can imagine, is only 1 meter long, so you'd have to move it 3 times to actually measure 2.600 meters. So when you were moving that, there'll be a greater uncertainty in that, so therefore you would have a bigger error in your results. So you've got to consider that. Now again, this makes the key point that your uncertainty in your values isn't just the resolution of the measuring device, it's also the experimental technique of using that measuring device. Next question. The interference of light can be observed on the screen when a set of double slits is illuminated using a suitable light source. Figure 5 shows the interference pattern observed on the screen. Explain how the interference pattern shown in figure 5 is formed. So pause the video now, then unpause the video when you want to go through your answer. Right, so let's think about how we could get 3 marks here. Well, this is an interference pattern, so you've got to talk about how interference occurs. So you'd have the idea that there's diffraction going on in the slits. Now there must be diffraction in the slits because it's a double slit, and therefore you get superposition and coherence. Now you will get constructive interference, which causes the bright fringes. You get destructive interference that causes the dark fringes. Now you're then going to talk about path difference and phase difference and how they produce your bright and dark fringes. So it's the idea that if they're in phase, you'll get a bright fringe. If they're out of phase, you'll get a dark fringe. Then your path difference, if it's a odd number of half wavelengths between the two path differences between the two waves, you'll get a dark fringe. Whilst if it's an even number of half wavelengths between the two paths, for your path difference, you'll get a bright fringe. You really need to learn how the phase difference and the path difference links to bright and dark fringes, constructive and destructive interference. Next question. The distance from the double slit to the screen is 3.5 meters. The spacing of the double slits is 7.3 times 10 to the minus 5 meters. Calculate the wavelength of the light used to illuminate the slits. So pause the video now, then unpause the video when you want to go through your answer. Right, so you can work out straight away what is going to be the fringe separation here. Well, you know the total distance between those is 0.24 meters, and between there you've got 8 fringes because you can count them. You can see how many there are. Now remember, you only count either the bright fringes or the dark fringes, so you get 8. So therefore, the fringe spacing is going to be 0.24 over 8, which is 0.03 meters. Now we know that lambda is equal to W, the fringe spacing, times by S, the slit separation, over the distance between the slit and the screen. So we've got all the other values, and we pop in our W, and we get lambda to be equals 6.3 times 10 to the minus 7 meters, which sounds about right because it's going to be laser light, so we're looking at that value of about 630 nanometers. Next question. Describe how you perform an experiment to make an accurate measurement of the wavelengths of monochromatic light. Your experiment should be based on the double slit interference technique and should discuss the choice of apparatus, the experimental setup, and how the apparatus is used. So pause the video now, then unpause the video when you want to go through your answer. Right, now once again, what you've got to think about is you've got to think about satisfying all the key points in this answer. So the first thing you've got to think about is you've got to think about a very basic method of what you could be doing. So what could you actually do here? So you talk about having your monochromatic light source, so it could be a light bulb which has a red filter from it or blue filter or whatever. You would then have your two slits, you then have your screen past your two slits. So you then got your very basic method of what you would do. So you turn on your light, you let the light go through the slits, and you would see the interference pattern form on the screen. Now what's very important is you've got to talk about all of the measurements that you would make. Now it's important to note that we want to be measuring W, we want to be measuring S, and we want to be measuring D. W being the fringe spacings, so you'd want to measure with a ruler the difference between the spacings on the screen formed, the slit separation, which you want to measure with a ruler between the two slits, and finally D, the distance between the slits and the screen, once again with a ruler, okay, measuring between the slits and the screen. Now again, you may think to yourself, what could you do in terms of which instruments you could use? Now you could use a meter ruler, I think, for the fringe spacings on the screen, a meter ruler between measure the distance between the slit and the screen. You may say vernier caliper, traveler microscope for between the slits, because it's a very small distance to be measuring, so therefore you want a small percentage uncertainty in your actual measuring values. Then finally, you want to think how you would get your values accurately. Now firstly, you would talk about maybe measuring multiple fringes and then measuring and then dividing it by the value of the fringes, like we did in the previous question, to then work out the value, which will have a lower percentage uncertainty because you're measuring a bigger number. So instead of saying I'll measure the fringe space between two fringes, I'll measure between 10 and then divide by the value, okay, and then you can work it out like that. You could then have a laser which allows the value of D to be quite big, because again you want the bigger the value, the lower the percentage uncertainty. So always think to yourself, A, how can I do a method to get accurate results? B, what values are going to measure and how am I going to measure them? What devices I'm going to use to measure them? And then finally, how can I make sure my values are as accurate as possible? And think about the practicals you've carried out in physics to do this. So, if we've been successful and learned in this revision session, you should be able to answer A-level physics examination style questions, assess your understanding on A-level physics, and understand what topics you need to improve upon for AQA A-level physics. So I hope you've enjoyed this revision session on waves, which is topic 2 for AQA A-level physics. Thank you very much for watching and have a lovely day.